because of the relationship between anti-differentiation and area under a curve, we started just using the integral sign to mean anti-differentiation if there are no bounds on the integral. So indefinite integration, anti-differentiation, same thing. For example, if we are trying to anti-differentiate x squared plus 1, we can just use anti-power rule, add 1 to our exponent, get x cubed, multiply by the reciprocal. 1/3 x cubed, antiderivative of 1 is x, and of course don't forget your integration constant plus c. Similarly, if we have e to the negative 4x, here you're doing a basic u sub. Your u is negative 4x, which means you're going to have to multiply by negative 1/4. The derivative of e to the u is just e to the u, so e to the negative 4x plus c. So really just some quick examples of anti-differentiation. Our favorite type of anti-differentiation, u sub, where you actually, I would recommend you use and write out your work for u sub on this one. Our idea for u sub is that we're trying to pick an inner function whose derivative is also part of the integrand. So picking x cubed plus 2 as our inner function, we see that its derivative, 3x squared, is also part of the function. All we have to do is multiply by 1/3. So this turns into 1/3 times the integral of root u du, and now that turns into an antiderivative that I know how to do. I'm going to treat root u like u to the 1/2. The antiderivative of u to the 1/2, add 1 to 1/2, I get 3/2. I'm going to be multiplying by 2/3 u to the 3/2 plus c, which I'm going to simplify then into 2/9 u, which is x cubed plus 2 to the 3/2. And then I add my constant of integration for my final answer. There's u sub with indefinite integration. Your u sub isn't going to be super hard on your final exam. It should be pretty easy to pick your u. Definite integration, remember, that's area under a curve, and that's when our integral has bounds on it. For example, if we want to find the area under the sine x curve from 0 to pi, the fundamental theorem of calculus says anti-differentiate sine x, which is negative cosine x, and then evaluate it by plugging in pi and 0. Negative cosine of pi is negative 1, just positive 1, minus negative cosine of 0 is negative 1, so plus 1. And we get an area of 2 under sine x between 0 and pi. Another example is finding the area under the curve 1 over x from 1 to e. All we have to do is anti-differentiate 1 over x. We get natural log of the absolute value of x, and we plug in e and 1. Natural log of e minus natural log of 1, we can simplify. We know natural log of e is 1. Natural log of 1 is 0. And so the area under the curve from 1 to e is exactly 1. The second fundamental theorem of calculus tells us that differentiation and anti-differentiation are inverse functions. So what this means is that if our function is the area under a curve between 0 and some point x, if we differentiate that function, we can really just take away the integral sign because there's no need to anti-differentiate that function just to integrate it back. So here I can just take the x, sorry, there it is, plug it in for t, and I get that f prime of x just equals x cubed plus 1. Remember that if you have an upper bound that's not just x, you do use the same procedure but you have to use chain rule. So you have to multiply by the derivative of that inner function. Here, if we're differentiating the integral from 0 to x squared of t cubed plus 1, we can just substitute in x squared for t, get x to the 6 plus 1, but we do have to multiply by the derivative of x squared. So we get 2x times the square root of x to the 6 plus 1. For our last example, I want you to notice the difference between this problem and the two before. In both of the problems that we have just done, we've been differentiating an integral. This problem down below does not tell me to differentiate. It just tells me to integrate. So that's what I'm going to do. The antiderivative of sine of t is negative cosine t, and I'm going to plug in x and 0. So this becomes negative cosine x minus negative cosine 0. So plus 1. I'm not being told to differentiate this function, which is why I just anti-differentiate like normal. But if I am told to differentiate either with an f prime or d dx, then I don't actually have to anti-differentiate just to turn around and differentiate again.